he actually, but he was a student a year ago. Now he's a young assistant professor at Barnard College. So Mark will just give us a short demo, which we will see as a poster or a talk, where he will tell more about how he and was working, and his group and collaborators working on optimizing CVC4. Mark, please.
Sure. Can everyone see the slides here?
Yes.
Yes. Okay, so I'll, because we're all virtual, I decided the poster didn't make so much sense. So I'll just go through some short slides, and I'll talk about how we can use neural networks to assist with this syntax guided synthesis. And this is joint work between myself, my advisor Ružica, my office mate Bill, and two wonderful students who are now undergraduates. So we just saw Andy's slide here, and he mentioned that static grammar minimization is one aspect where there's some space for optimization. So I'll talk about grammar minimization in the context of using machine learning. So for those of you that didn't catch last week's talk, maybe just to review, SyGus, we have a SyGus solver and we feed it some specification and we get back out code. So that specification consists of two main parts, constraints and a grammar. So let's take a look at a specific example. So here, this is in the SyGus language, a specification that says we'd like some function that maps hello to hello, hello. So you can tell really easily here that the function we're looking for is to concatenate the input with itself. And indeed, if we run our solver, then that's the function that we're going to get. Now, what's interesting is if you take a look at the grammar, we didn't actually need 90% of this grammar. We only needed a small portion of it. So the question is, can we predict ahead of time what parts of the grammar we don't need and statically minimize that grammar in order to shrink our search space? And so what we're going to do is try and take our specification and then construct a filtered grammar. So to do this, we're going to have to introduce three different components for this grammar prediction. We're going to introduce criticality, and this is saying how likely is it that a particular terminal is part of the grammar that we need for this particular function. So this is where we're learning something about the semantics of the SyGus language. And then we also need to predict the time. And what's interesting is that predicting the time is solver specific. So we're actually trying to use machine learning here to predict something about that particular solver and the way it explores its terms. And then we'll combine these two metrics to filter out our grammar. So we have three main components here. Our criticality, where we're building a map between IO examples. And for this whole presentation, I'm focusing just on programming by example for SyGus. I'll talk a little bit about how that's a restriction. But we're trying to create a map between IO examples and terminals and say, what's the probability that this grammar terminal is required for solving a SyGus query that describes this IO programming by example constraint. And then for predicting time, we're saying, okay, just in general, how much time does it add to our solver if we include this new terminal? So if we were to remove this terminal from the grammar, let's say we're using CVC4, how much time could we save by removing this terminal from the grammar ahead of time? And then to combine these, we're going to take our prediction for the probability of criticality and then the time saved over the size of the grammar and filter out our grammars. So three main questions are, what's the probability a terminal is critical for this particular constraint? What's the estimated time saved by removing this particular terminal? And then we finally ask, of the terminals that save the most time by being removed, which are the least likely to be critical? Now, this is just a poster presentation, so I won't get into all three of these, but I'll talk a little bit about this first one, criticality. And the key question here is how we obtain training data for this. So we're going to be using a neural network, and I'm sure everyone's heard the basic story behind neural networks by now. We feed it some training data, and then we can give it more data, and it's going to give us a prediction. So here, our training data is going to be sets, triplets of input-output examples, the input and the output, as well as the terminal, mapped to whether or not the Boolean value of whether or not that terminal was critical for that example. So in order to generate this data set, we take 3 steps. First, we generate functions from the grammar, and we use this enumerative solver that Andy was just talking about, SyGus CVC4 we use specifically because it's so beautifully engineered and so easy to use. In particular, there's one flag, SyGus stream, which will just stream all the possible functions that meet the constraints. And if we run SyGus stream with a grammar with no constraints, we can just enumerate through all of the possible functions of that grammar. And then we're going to apply, for each function, we're going to apply that function to some randomly generated inputs. So as an example here, we take this third function, x plus x plus x, and we say, okay, we're just going to give it some inputs and outputs. And then we're going to build what's called a one-hot vector. And this is a sort of machine learning thing. And it just says we want to count up how many times the terminals were used for this example set. So for the example, our triplet here is going to be rand, and then rand will be the second part of the triplet, and the third part of the triplet will be the set plus plus, string plus plus. And that's going to map to 1. And then everything else, all the other terminals are going to map to 0 because we didn't require any of the other grammar terminals for synthesizing a function that meets this constraint. So once we've built this, we build what's called the one-hot vector, and then we can pipe this through a normal neural network. We use something called a feed-forward network, but actually this is not a critical part of this. So quickly hop to the evaluation then, because we've only got 5 minutes here. So we looked at SyGus comp, which is the SyGus competition. Rajiv was telling us a bit about this. Within the SyGus competition, there's a number of different tracks. I think there's 5 tracks in 2019. And the PBE strings track is one of those. So programming by example for strings, there's 64 examples. And solvers get an hour to solve each problem. And so we ask, can our grammar reduction tool, GRT here, working with CVC4 outperform CVC4 by itself? And the short answer is yes, 47% faster to add this grammar reduction tool in front of CVC4. What's really, and so you can see this is just a selection of some of those benchmarks which had a reduced time. What's really interesting is that when we only consider the criticality, when we're only predicting whether or not a terminal is critical to the grammar, and we don't take into account the timing data, synthesis succeeds on only 11 out of the 64 benchmarks. So the idea here is if you're removing a terminal from your grammar, you want to be really sure that you're actually going to save time with this, because the risk that you run, of course, by removing a terminal from the grammar is that synthesis can no longer succeed because your grammar is too small. So sort of the key insight here is you need to actually consider both how much time you're going to save, what's the reward, as well as what is the risk. So we saw in 32 out of 64 benchmarks, we were faster. And there was even one benchmark which was timing out with CVC4, which we were able to actually solve within the timeout, the standard timeout of the SyGus competition with our grammar reduction tool. So there's a lot of really interesting future directions. You might look at this and say 46% faster. Oh, maybe we're done. That's as good as machine learning is going to get. But I think there's a lot of space here. The key insight so far is just that we need to account for not only the criticality, but the time savings. But if we're looking more generally, maybe there's some more sophisticated time prediction heuristics. As a reminder, we only looked at one terminal, how that terminal behaves across all sorts of different constraints for that tool, but we might be able to have a more fine-grained time prediction. Also, each example is encoded separately. So we were only looking at programming by example, and we saw We looked at each constraint, programming by example constraint, individually, and then gave that to the neural network. That doesn't account for any interaction between the constraints. So we might be able to learn something more if we looked at how the input-output examples interact with each other. The other question, of course, is so far we only looked at strings. Strings, as it turns out, are very easy to encode in a neural network. But as we start branching out to integers, bit vectors, and data types, the encoding process becomes a bit more complicated. And additionally, we were only looking at programming by example. And so the question is how many, but of course, SyGus in general and CVC4 supports more general first order logic constraints. And so how might we encode these logic constraints into the neural network instead, as well as the programming by example? So if you'd like to read more, we had a paper at this at AAAI last year. This was actually in February last year, right before everything went south. The code is also online. So I'd encourage you to take a look at this. And the other thing I just want to point out is that there was some interesting work that came out a bit after this on a similar problem that extended the idea of using machine learning to pre-prune the grammar. That was more general than just looking at programming by example constraints. And so maybe we can even hear a bit about that from our next speaker.
Okay, thank you, Mark. That was a couple of minutes more. We can allow only one quick question if there is some. Let's see. Radu, it has to be quick.
Yeah, what about transformers for this job?
Yeah, so we were looked at really the most basic neural network, which is just a feed-forward network. And we had a lot of questions about this on the review as well, because we submitted to AAAI, where there's a lot of machine learning people. So there's a lot of other techniques out there that might be more effective. I think and we definitely don't have the most efficient neural network structure yet. I think the key point here is just that if you're going to do some pre-filtering, you need to think about two things, not just how critical the grammar elements are, but also how much time you're going to save.
Yeah, so it looks to me like you need some kind of attention mechanism in this. I mean, that might be kind of, and that's what transformer also have, self-attention, and and you can think of it also as you take a grammar and you generate a new grammar, like a, like a translation thing. So I think there is some. I don't know whether it would help, but there might be some potential here.
I have to look at it, possibly. Yeah, a lot of space there.
Yeah. Very nice, by the way.
So we need
very cool.
Thank you too, but we really need to take a short break now. Let's start wherever is your time zone at 05. And Elizabeth, if you're there, let's make sure that your slides are working right now.
Yeah, great.
Thank you, Mark.